Okay, so from the point of view now of superposition, we want to find the voltage drop across the 2 ohm resistor, and it has a contribution from each of the 4 sources. So what we want to do is analyze the circuit from the point of view of each of the 4 sources, which means we have to do it 4 times. When we treat one source, we will replace the other sources by their internal resistance. So when we start off with the 40 volt source, we will replace the 2 current sources by an open circuit and the 60 volt source by a short circuit, as that is the internal resistance appropriately. Okay, so here I have redrawn the circuit from the point of view of the 40 volt source. Now, remember that we need to include all resistors basically that are not eliminated by our changing a source to its internal resistance. So, on the left, the 20 ohm resistors in parallel with the 40 volt source, so that one of course stays. Up on top here we have a 6 ohm, we have 2 ohm, which we're looking for the voltage drop across. So I've indicated that that voltage there is V prime. Well, the prime is off the screen, but that's okay. Now, so this 3 ohm resistor here in this branch, no current will flow through him now because he's in an open circuit piece. And the reason for that is, look, the 12 of the source that was there, 5 amp source, forces the current through there to be 5 amps. So the other sources won't contribute to the current through the 3 ohm. Okay, so he's not going to be part of the 40 volt analysis. Okay, so over here on the right, this branch is also open, so we'll leave that out, although there's no resistors in it, so it don't really matter. On the bottom where the 60 volt source is to, we've indicated a short down there. So that just means take the source out and continue the circuit through there. So in this branch now, we have 12 ohms. So we've redrawn the circuit to simplify it a bit. And so we've included the 4 in series with the 8. And in addition to that, so let me say first then that, okay, we're going to combine these. They are in series, so 4 in series with 8 is equal to 4 plus 8, or 12 ohms. This one, we're ignoring this one, right? Up top here, we have a 6 and a 2. And so 6 in series with 2 is equal to 6 plus 2, of course. And we have 8 ohms. Now, in addition, we'll eliminate this part here. So when we redraw the circuit, got our 40 volt source, the 20 ohms. In the top now we've indicated 8. When we've taken out this branch with the 3 ohm in it and the branch that had the 12 amps in it, it simplifies this portion of the circuit here, and we've replaced this branch down here with 12 ohms. Now this circuit looks a little bit strange here, but one of the things you got to notice is that, look, all of this here is at the same potential, and so these two are in parallel, and these two, of course, the absence of a connection here says that these two are in series. So to further simplify this circuit now, we want to combine these resistors, because remember, we're going for RT here. So we want to say now that we have 8 in series with 4 equals 12. We have 12 in parallel with 24, and so that gives us 12 times 24, product over sum, right? Over 12 plus 24, 36. And if you do the math there, it comes up with 8 ohms. Okay, so now this circuit's getting a bit simpler. We got up top 12 ohms, so I've drawn it on the side over here. Remember now that this one is going to be now 8 ohms. Replace these two, and the left side of it connected to the bottom of the source, right? The right side of it connected to the 12 ohms. So this is appropriate, right? Okay, now over here we are trying to find a current that goes this way, and so let's think about our original circuit. From the source, the current that goes this way is this current here, and because there's no connection here, that current also goes through the 2 ohm and comes over here and goes down through the 4 ohm. In fact, if we look at it here, there's only a series branch that current goes through before it divides here. So we don't need to include this 20 ohm in the calculation. In fact, we could say that on this side over here, we certainly have 20 ohms. 8 in series with 12 is equal to 20. And we could go ahead now and say that RT is 20 in parallel with 20. But again, you know, because the source is in the middle, there's 2 resistors in parallel with it. We only want to consider this current going this way. And we have 40 volts across 20 ohms. And so let's call that current there I prime. And I prime then is equal to 40 volts divided by 20 ohms, and that is 2 amps. Okay, so 2 amps leaves the source, goes right. 2 amps leaves the source, goes right. So 2 amps there. And again, back to our original circuit, right? The 2 amps comes here and goes through this. And so the reason why we want to talk about that is because back in that original circuit now, I'm trying to write a V there. V prime is equal to I prime times R, which is 2 ohms. And we say that the current enters the positive end of the resistor. So the direction of current and the polarity marked for V or V prime agrees. So this is a positive sign down here, plus 2 amps times 2 ohms. So that means that V prime is equal to 4 volts and plus 4 volts. Okay, so that is the contribution of the voltage across the 2 ohm resistor from the 40 volt source. So now we move on to the next source. And the next source that I decided to do is the 5 amp source. Now, I mean, you do these in whatever order that you like, right? And so one of my circuits is off the screen there, I guess. And so let's pull it back in for the screencast part, put it there. Now, so once we tackle this one, the 5 amp source, again, the 12 amp replaced by an open circuit, the 60 volt replaced by a short circuit, and the 40 volt replaced by a short circuit. So, got the same thing down here, right? These 2 resistors are now in series. We're going to remove this part over here because it has no bearing on our circuit anymore, because there's no current over there. And let's think about what this does. we have a short circuit across the 20 ohm resistor. And basically what that means is that there's no voltage across the 20 ohm resistor, so there's no current through it. And so that means that we eliminate the 20 ohm from the circuit. And again, the reason for that is that 20 ohm resistor is directly in parallel with the 40 volt source. So the voltage across him is set by the 40 volt source. They don't get a contribution from any of the other sources. We can calculate the current through there as 2 amps. And so that part of the circuit, is only affected by that 40 volt source because it's directly in parallel with it. And so what that means is that, again, the other sources don't contribute to the voltage across there or the current through it. And so we won't include that resistance in any of the other circuits except for that first one. Okay, so now if we want to redraw this, maybe the first thing we should say is that, again, we got down in that bottom piece 4 in series with 8, and that gives us 12 ohms. So as we redraw the circuit, we're going to get rid of the 20 ohm, we're going to replace this bottom branch by a 12 ohm, and we're going to get rid of this over here. So we got our 12 ohm, we got our 24 ohm, we got the 3 ohm and the 5 amp branch, we got 6 ohms over here, and over here you see where I put in the 6 ohms. Again, these two here now are in series, and so we had 2 in series with 4, and that equals 6 ohms. Okay, why are the 2 and 4 in series? Because no current goes over here. This is open. We took that out. So over here on this right side, we have those 2 resistors now that are in series. So 6 ohms. Okay, so now let's look at this one. The only simplification really that we can make here is that these 2 are in parallel. And again, right, all this here, including this, is at the same potential. And all this here is at the same potential. And so these resistors are directly in parallel. And we have, again, 12 in parallel with 24 is equal to 12 times 24 over 12 plus 24. And we did that calculation before, come up with 8 ohms. So we put the 8 ohms in now from this connection point to this one. So that's here. And again, right, if we look at this, is the current going this way that we're interested in, because the current through this 6 ohm is the current through our 2 ohm over there. Comes out of the source, goes left. The 6 ohms on this left side, we don't need to worry about that. We're worried about the current going this way. Okay, so the current in this branch, we have 8 ohms in series with 6 ohms, and that gives us 14. And so you'll notice that I redrew the circuit here to show this branch, that's 14 on this side, 6 on this side. Now again, right, we could go through this and find RT, but we don't need to, because we're just interested in this current. And we can find it by current division. Okay, using current division, Ix is equal to Req over Rx times It. And when you're doing this, all right, you got to be very careful about the Req, because it's not usually the total resistance of the circuit. What it is the resistance that the current divides between. Now, all of the 5 amps goes through the 3 ohm, so he's not included in Req. It's the resistance that the current divides between, which is the 6 and the 14. Now, 6 is smaller. Most of that 5 amps going this way. The one we're interested in is this one. So that one for us is Ix. So that means that this 14 is Rx, and for this calculation, Req is 6 in parallel with 14. And so that is equal to 6 times 14 over 6 plus 14. And so if you do that, 6 times 14 over 20, and REQ comes out to be 4.2 ohms for REQ. Now, so that means then that IX is 4.2 over 14 times IT, which in this case is 5 amps, and IX is equal to 1.5 amps. Okay, great. So the 5 amp comes up here, divides at this point into 1.5 amps that goes our way, and a current that goes that way, which KCL will tell us 3.5. Okay, so it's the 1.5 going right that we're concerned in. Got 1.5 here then, got 1.5 here then, and so got 1.5 here, right? So from this original circuit then, we can say that V double prime is equal to IX multiplied by the 2 ohms. Again, the direction of IX entering the end of the resistor marked positive is in agreement, and so this is a positive number, plus 1.5 amps times 2 ohms, and V double prime is equal to plus 3 volts. So now that means basically that we're half done. Okay, so 2 sources left to think about, and the next one that I decided to do was the 60 volt source. And of course you can do them in whatever order you like, and so now my redrawn circuits now, again, let's think about what happens when we consider the 60 volt source. The 5 amp source, open circuit. You notice over here, got my 40 volt source short circuited, and I've omitted the 20 ohm resistor that was over there because I got the same scenario as before. We're also then going to scratch out this fella here, and we're going to scratch out this here. This time on the bottom, we're not going to make a simplification with the 4 and the 8. Not yet, anyway. And so you can look at this, got the 24, got the 4, you know, I didn't, you might have a look at the fact that now all of this here is the only path for current to go, so 3 of these are in series, and you could make that simplification. But you'll notice that I just redrew the circuit without making any simplification there. I just took out the branches that is not required, and I drew this, right? So my 24 volts, now think about the fact that all this is out. The 24 volts is basically in parallel with this branch down here and the top branch. And so my V triple prime still shows up in this circuit, and 3 of these resistors here are in series. So we have 6 in series with 2, in series with 4, and that gives us 12 ohms. And so now you'll notice that here we got 12 in parallel with 24, which happens by coincidence because we got that calculation done, but it was a different 12 that we used before. Not that that's an issue. 12 in parallel with 24, and again we've done that calculation a couple of times now. Got 8 ohms for that. So we put our 8 ohms in, and now we have in this circuit our T is equal to 4 plus 8 plus 8, and our T then is equal to 20 ohms. And that means that IT is equal to V divided by RT, so 60 volts over 20 ohms, and that is 3 amps. Now, the 3 amps comes out of this source here, goes through this. So that means in this circuit we have 3 amps. In this circuit here we have 3 amps. And we want to find the piece of the current that goes through the 2 ohm resistor. And so this one, if you would. Now I'm going to switch to blue, and let's call this fella here now IX. And we want to find IX by current division again. And so let's say then that IX is equal to Req over Rx times IT. And this time, right, the 12 ohms is Rx, because that's the branch resistor we're trying to find, and Req is the 12 in parallel with 24, so this 8 ohms right here is Req. So Ix then will be 8 divided by 12 multiplied by IT, which was 3 amps, and Ix is 2 amps. So that means that in this circuit here we have 2 amps, and so we have right here 2 amps. Now this 2 amps is contrary to the polarity we have for V triple prime. And so that means V triple prime is going to be negative. So V triple prime then is negative 2 amps multiplied by the resistance 2 ohms, and that means that V triple prime is negative 4 volts. So one source left. So let's tackle the 12 amp source now. And this time I've made the circuit, the first circuit, a bit simpler. And again, now you got to visualize that we kept the 12 amp source over here. We took out the 60 volt source on the bottom and combined the 4 and 8 into 12 ohms. The 24 ohms then is in parallel with that 12, just as it has been in some of the previous circuits. Over here, remember there was a 60 volt source that we shorted out, and that took out the 20 ohm resistor, so that part on the left is gone. In the middle here, we took out the 5 amp source and the 3 ohm resistor branch, just like we did in previous circuits, because it's open. And so, you know, you should be able to visualize now that we got from that original circuit with the pieces that were shorted and opened, and we came up with this. Okay, so based on that then, we have these two here are in series, and so again 6 in series with 2 is equal to 8 ohms, and that 8 ohms is here. We have these two in parallel, and we know now that 12 in parallel with 24 is also 8 ohms. And that 8 ohms then becomes this one. So here now, we have these two 8 ohm resistors that are in series, right? And so these two here, now one path for current to flow through them, And so 8 in series with 8 is equal to 16 ohms. And we have 12 amps comes out here and divides into that 16 ohm and that 4 ohm. And so we want to find this current right here, which I guess we'll go ahead and call X. So in this one, we actually do need to kind of define RT because the 12 amps divides into this 16 ohms and this 4 ohms. And so remember now that that 16 ohms over there, or this 16 ohms right here, is our X, and REQ then will be RT in this case, which is 4 ohms in parallel with 8 ohms. And we have then 4 times 8 over 4 plus 8, which is 12. And that becomes 32 over 12. And of course, I'm using 8. I didn't redraw the circuit, and that's why I guess I made that mistake. But it's actually 4 in parallel with the 16, you know. This is the branch resistance over there, so it's 4 in parallel with 16. So I got 4 times 16 over 4 plus 16, which is 20. So that's actually 64 over 20, which is 3.2 ohms. So for that circuit, then my X is equal to REQ 3.2 over RX, which is 16, multiplied by IT, which is 12 amps, and IX is equal to 2.4 amps. And so the 12 amps divides here. Most of the current goes through the smaller resistor. IX becomes 2.4. Now, over here then, in our original circuit, the 12 amps divides into 2.4, and our IX, oh, I'm sorry, our IX is 2.4, and the rest of that current then goes down through the 4 ohm resistor. And so V4 prime then is equal to, now again, the polarity on our Vx or our V4 prime here is contrary to the direction of that current, so it's going to be negative, and it's going to be 2.4 amps multiplied by 2 ohms, and that gives us negative 4.8 volts for V4 prime. Okay, so we have all of our voltages now: V prime, V double prime, V triple prime, V4 prime, and so on. And so, okay, I got a mistake made there somewhere. Where is it? Oh no, I don't actually. And so now let's go back to our original circuit then, and this is it, right? And remember now that Vx is got a contribution by each of the 4 sources, and we calculated them individually. For V prime, we had 4 volts, and specifically plus 4 volts. For V double prime, we had 3 volts. For V triple prime, we had negative 4 volts. And for V4 prime, we had negative 4.8 volts. And so conveniently, I guess we say that the plus 4 cancels with the negative 4, and so we're left with 3 minus 4.8, negative 1.8 volts is Vx. Now, and so, you know, we could come up with the same result from any of the other methods. Maybe superposition is easiest for that circuit, is a kind of a complicated circuit. And remember that the negative polarity on this suggests that, you know, the net current or the total current to that resistor actually goes through this way. And that means then that the reality is that is plus minus 1.8 volts, right? And so the actual polarity of the voltage drop across there is opposite to that from what was first assumed. And you know, the assumption, your initial assumption is arbitrary, because when you look at that network, you're not sure what way the current goes through there, so you don't know the polarity. And so this gives you very specifically then the final polarity as well.